A sheet of steel enters a machine as nothing more than raw material. Minutes later, it emerges as hundreds of perfectly shaped components with tolerances measured in fractions of a millimeter. No saw blades, no cutting fluids, no physical contact. Just a concentrated beam of light powerful enough to slice through metal. Inside modern manufacturing plants, CNC laser cutting systems are transforming the way products are made. From automotive parts and aircraft components to industrial machinery and consumer electronics. These machines perform operations that would have seemed impossible just a few decades ago. But how can a beam of light cut through thick steel? What happens inside these highly automated systems? And why are manufacturers around the world investing billions into laser technology? Today, we're taking a deep look inside the fascinating world of CNC laser cutting. CNC laser cutting is one of the most important manufacturing technologies in modern industry. The process combines advanced computer control with highly concentrated laser energy to cut, engrave, and shape materials with extraordinary precision. These machines are found in automotive factories, aerospace facilities, construction equipment plants, electronics manufacturing centers, and countless fabrication workshops around the world. What makes CNC laser cutting so valuable is its ability to produce complex shapes quickly, accurately, and repeatedly while minimizing material waste. A single machine can process thousands of parts every day while maintaining exceptional consistency. In this documentary, we'll follow the entire process from digital design and raw material preparation to laser generation, automated cutting, quality inspection, and final industrial applications. Along the way, we'll uncover the engineering innovations that make laser cutting one of the most powerful manufacturing technologies ever developed. Long before a laser begins cutting, every component starts as digital information. Engineers create detailed CAD models that define every dimension, hole location, bend line, and contour. These designs are transferred into specialized CAM software, where cutting strategies are generated automatically. The software determines the most efficient cutting path, reducing travel time while maximizing material utilization. This process, known as nesting, arranges parts across a sheet to minimize scrap. In large manufacturing facilities, hundreds of components may be nested onto a single metal sheet. Even small improvements in nesting efficiency can save thousands of dollars in material costs every year. The software also calculates piercing locations, cutting speeds, laser power settings, and gas requirements. Every movement is optimized before the machine begins operating. What appears to be a simple cutting operation is actually the result of thousands of engineering calculations occurring behind the scenes. The process begins with large sheets of steel, stainless steel, aluminum, copper, brass, or other industrial materials. These sheets may weigh hundreds or even thousands of kilograms. Automated loading systems use vacuum lifters and robotic handling equipment to transport material from storage towers to the cutting machine. Modern fabrication centers often operate around the clock with automated material storage systems that can hold dozens of material types. As a new sheet enters the machine, sensors verify thickness, dimensions, and alignment. Positioning accuracy is critical because even tiny errors can affect hundreds of parts being produced from a single sheet. Before cutting begins, the machine automatically establishes reference points and calibrates its positioning system. Only after these checks are completed does the laser come to life. At the heart of the machine is one of the most remarkable tools in manufacturing, the industrial fiber laser. Unlike traditional cutting equipment, laser systems generate an extremely concentrated beam of light capable of delivering enormous amounts of energy to a tiny area. Inside the laser source, electrical energy is converted into optical energy. Specialized optical fibers amplify the light until it reaches cutting power levels measured in thousands of watts. Some industrial fiber lasers exceed 30 kilowatts of output power. The laser beam then travels through protected optical pathways toward the cutting head. What makes this technology extraordinary is the concentration of energy. The beam can be focused to a spot smaller than a millimeter while carrying enough power to instantly melt or vaporize metal. At that moment, the machine is no longer using force to cut material. It is using pure energy. As the cutting head moves across the sheet, the focused laser beam strikes the material surface. Temperatures at the focal point rise rapidly, reaching levels high enough to melt or vaporize metal almost instantly. Assist gases such as oxygen, nitrogen, or compressed air are simultaneously directed through the nozzle. These gases perform multiple functions. They remove molten material, cool surrounding surfaces, improve edge quality, and increase cutting efficiency. The CNC control system coordinates laser power, cutting speed, focus position, and gas flow in real time. Thousands of adjustments occur every second. When cutting thin sheet metal, the machine can move at astonishing speeds. Some systems process dozens of meters every minute while maintaining exceptional accuracy. Complex shapes, tiny holes, sharp corners, and intricate patterns are produced without changing tools. Every movement is guided by digital instructions with remarkable precision. Modern CNC laser cutters are far more than powerful cutting machines. They are intelligent manufacturing systems. Advanced sensors continuously monitor beam quality, cutting conditions, nozzle alignment, temperature, vibration, and positioning accuracy. Artificial intelligence and machine learning are increasingly being integrated into production environments. Some systems automatically adjust cutting parameters when material conditions change. Others predict maintenance requirements before failures occur. Robotic unloading systems remove completed parts, while scrap skeletons are automatically separated and recycled. In highly automated facilities, entire production cycles can operate with minimal human intervention. The result is greater productivity, reduced downtime, and consistent product quality. Precision is one of the biggest advantages of CNC laser cutting. Manufacturers often work with tolerances measured in tenths or hundredths of a millimeter. After cutting, components undergo detailed inspection procedures. Laser scanners, coordinate measuring machines, and automated vision systems verify dimensions and detect defects. Surface finish, edge quality, hole geometry, and overall dimensional accuracy are carefully evaluated. Any deviations can be traced back through digital production records. This level of traceability is especially important in industries such as aerospace, medical manufacturing, and automotive production, where reliability is critical. The ability to repeatedly produce identical parts is one reason laser cutting has become indispensable across modern industry. Few manufacturing technologies serve as many industries as CNC laser cutting. Automotive manufacturers use laser cut components for chassis structures, brackets, exhaust systems, and body panels. Aerospace companies rely on precision-cut parts where weight reduction and accuracy are essential. Construction equipment manufacturers produce heavy-duty steel components for machinery operating in extreme conditions. Electronics companies use laser cutting for enclosures, mounting systems, and precision metal assemblies. Even architectural firms utilize laser-cut materials to create decorative structures and complex building features. From everyday products to advanced engineering systems, laser-cut parts are everywhere. Most consumers encounter them daily without ever realizing how they were made. Laser technology continues to evolve at an incredible pace. Higher power fiber lasers are enabling faster production and thicker material processing. Automation systems are becoming smarter and more autonomous. Digital factories are connecting laser cutters directly to enterprise software, inventory systems, and production scheduling platforms. Future machines may automatically optimize production in real time using artificial intelligence. Some manufacturers are already experimenting with fully autonomous fabrication cells capable of operating continuously with minimal supervision. As industries demand greater efficiency, flexibility, and precision, laser cutting technology will play an even larger role in global manufacturing. Every precise component, every intricate pattern, and every perfectly cut metal part represents the convergence of engineering, automation, and advanced physics. CNC laser cutting has transformed manufacturing by replacing traditional mechanical processes with extraordinary precision and efficiency, powered by concentrated light. From massive industrial factories to specialized fabrication shops, these machines help build the products, vehicles, infrastructure, and technologies that shape modern life. And as automation and laser technology continue advancing, the capabilities of these remarkable systems are only beginning to unfold. If you enjoyed this deep dive into industrial technology and want to explore more of the world's most fascinating machines and manufacturing processes, be sure to subscribe to Machines Hub and join us for the next engineering documentary.